Let us start lecture 30 and the broad topic of course passivation and mixed potential theory. We have considered one case studies like increase in concentration of oxidant and then after reaching to a final high concentration decreasing the concentration gradually in the same path, and then also we have seen the influence of mechanical disturbance of the passive film after reaching the region or the concentration where the mixed potential, that is particular that concentration polarization and this cathodic polarization plot is cutting across the anodic polarization plot at 2 or 3 locations. So, there we could see that if we do a mechanical disturbance of the passive film, instead of maintenance of passivity, we can increase the corrosion rate because of the breakdown of the passive layer. Now, if we recall, so lecture 30 topic it is same as last one, passivation and mixed potential theory, and here we will be now try to see the few more case studies. And before we go to the case study, second case study, let us analyze Faraday's experiment. The Faraday's experiment on passivation. Of steel in HNO3. Now, in that experiment, if we go back and see that experiment, initially iron block is put in a concentrated HNO3 which is around 70% concentration. So, there initially there will be a little bit of bubble formation on the iron surface and then immediately the bubble formation vanishes, and then if we see the wet loss due to the corrosion effect, we see that there is negligible wet loss. Now, after that what was done, in the same beaker if we add water and then keep diluting the HNO3 solution, we see that still there is no noticeable change in the wet loss. Now, if we go to a very dilute HNO3 solution, the system shows no wet loss. So, that point we say that initially when it was dipped in acid solution, concentrated acid solution, it went into passivation and then it remained passive when we change the concentration from high to low. Now, after that in the dilute HNO3 solution, if we shake the particular beaker or if we do with a glass slide, if we just scratch the top surface of the iron object, we could see that the vigorous bubbling starts and we could see that the wet loss is noticeable now due to corrosion. So, this is the phenomena which can be solved after understanding the effect of concentration of oxidant from high concentration to low concentration, and addition to that is the mechanical disturbance of the passive layer. So, in the last case what happened, if I go back to the last one, if I try to see that when we see the blue one, this blue curve, at the 6th point when we reduce the concentration from let us say concentration 8, it is spontaneously passivating. But as we decrease the concentration, when it reaches to concentration 6, if we do not disturb, the passive current density will be the corrosion rate. But if we disturb the surface with a mechanical effect, scratching or other means, then the corrosion rate immediately moves to the point which is this one, which is nothing but I critical. So, this exactly happens in case of HNO3. Now, in case of HNO3, the reaction, the oxidation, this reduction reaction, we can say that NO3 minus plus 4H plus 3 equal to NO plus 2H2O, and that is what when we scratch the iron block, when it was taken from a high concentration to low concentrated HNO3, we see the NO gas, that is this nitrogen oxide gas is present there. So, that bubbling is nothing but because of this particular gas, this is a gas phase that happens, and this E0, E naught for this oxidation reaction. So, I can say that HNO3 minus NO, I can say, because here it is. So, this is this value is plus 0.96 volt with reference to SHE, and if we consider E0 for iron equal to minus 0.44 volt with reference to SHE, which is standard hydrogen electrode. Okay. So, if we see the interaction, iron has got its own active passive transition mode. This is the iron plot, iron active passive polarization plot, log I, which is ampere per centimeter square. Now, when the concentration is very high, the cathodic polarization line is cutting at this location. So, this is E equilibrium for this reaction, let us say R1 is the reaction R1, and this is E equilibrium of iron, I0 of iron over iron surface, this is I0 of reaction 1 over iron surface, because that reduction process is also taking place on the iron surface. So, I could see that it is achieving spontaneous passivity, and if I see the passive polarization plot, the polarization plot will look like this. Okay. Now, if we decrease the concentration, so now I am changing the concentration, and let us say this particular location, that means I0 does not change. So, it goes like this. And then it comes here like this. So, okay. So, if we see those concentrations, so as this potential is decreasing, the concentration of oxidant decreases, and here oxidant is of course this one. So, this oxidant decreases, and if it decreases, I could see that when it decreases to, let us say C1, this is C0 initial concentration, this is C1, this is C2, and C1 and C2, if we do not disturb, it will maintain those passivity. Okay. Now, at this location, at this concentration, if I scratch the surface, then where will be the point where mixed potential should be maintained. So, the point will move from this location to this location. So, this location comes when we have mechanical scratching, but if we do not scratch, the system would maintain I passive, which is nothing but I core. So, it will maintain passivity, and I core is of course very low when it is equal to the passive current density. But once we disturb, because when it is C2, that time it is actually going through 3 locations where I C equal to I A, but it will maintain this point. If it is not disturbed, if it is disturbed, it will come to this. It is a similar discussion what we had in the previous case, where we changed the concentration of oxidant from high to low and then coupled with mechanical disturbance. So, we could see that the corrosion rate initially it was here and then it is moving to this particular equation. This is I corrosion prime. So, I corrosion prime is very large compared to the I corrosion close to I P. So, we could see this particular reaction would happen at a very high rate, which is equal to this one. So, at this location IC of this particular reaction 1 equal to I core prime. So, that is what the corrosion rate increases if we scratch the iron block in the dilute nitric acid solution after it is passivated. Remember, after it is passivated. If it is not passivated, if we put it in dilute nitric acid, then of course, it will corrode at this particular rate. Okay. And when it reaches to the concentration C1, then only the passivation happens. So, that is what when we put the iron block in the HNO3 solution, the concentrated HNO3 solution, initially we do see little bit of bubbling, because that time this particular potential and this potential, they are trying to drag both of them and to a particular mixed potential, which is nothing but this, and then only passivation appears. So, initially when this particular potential is dragged to higher location, it will move in this fashion. Then only it reaches here. So, before that, when it moves like this, until unless it reaches to this location, you will have a little bit of vigorous gas formation, which is this. That means vigorous, this particular reaction rate would be higher, because the anodic dissolution rate is also higher, since it is moving in this location, in this particular pattern. So, this will follow this anodic polarization line. So, this is the understanding of Faraday's experiment on passivation of steel in HNO3 with reference to mixed potential theory. So, let us take up case 2. Case 2, let us see the effect of concentration polarization of cathodic reaction on the passivity of an active passive metal. So, we have seen in case of a condition where the cathodic reaction is concentration controlled and anodic reaction is activation controlled, that the dissolving metal is going through activation control mode, we could see that corrosion rate at certain point it becomes constant. But that case, if this is voltage, so if this is my So, this is IL1, IL2, this is IL3, IL4, and it happens when velocity increases. We have seen that anodic, this ox, this is my ox plus E equal to red, this is the reduction process, and it is reaching limiting current density at a different location with increase in velocity. So, one velocity, let us say velocity 1 is less than velocity 2, like that it moves, and that case delta 1 would be greater than delta 2, greater than delta 3, greater than delta 4, and this delta is nothing but IL equal to NF dNF C0 by delta. This is the basic equation, and since we are considering E, which is 1 electron, so this will be 1, fine. So, now this delta, which is the boundary layer, diffusive layer, so that it decreases as we increase the velocity. So, now in case of active metal, if this is the condition, so now so this is IL5, so V5 and then delta 5. So, all other factors are same if we start with the same concentration every case, and if it is at a temperature T, which is let us say room temperature. So, this will be the situation, and then if we try to see the corrosion rate as a function of velocity. So, these are the points where I could maintain mixed potential theory, but once it crosses our V4 velocity, once we go to V5 or V6, if we have IL6, which is delta 6, this is V6, it does not matter that with all the other velocities apart from V4, the corrosion rate would be at this point. So, the corrosion rate increases and then it remains constant. Now, this is the situation where active portion of the dissolving metal. So, this is M minus Ne equal to Mn plus. So, this is polarization IA. So, in case of that, corrosion rate initially increases and then it remains constant. But what will be the situation if this interaction is with active passive metal? So, in that case the situation would be the situation would be very different. So, this is log I, this is voltage. In this is case when active, we are considering active metal. And in this case, this is active passive metal. In that case, let us see what will be the situation. So, if this is the active passive anodic plot, and of course, all the points are there. So, this is ECP equal to EPP in this particular situation. This is I critical, this is E equilibrium of that metal, this is I0 metal over the metal surface. Now, if we see a cathodic plot, let us say this is the cathodic plot, and now this is the IL 1. Now, after a very high current density, this is IC, this is IA, and this corresponding to OX plus E equal to reduction, this particular reduction process, and here it is reaching limiting current density. So, if we this corresponding to some V1 speed of the V1 velocity of the solution. So, if we reduce the V1, then of course, this particular factor will increase. So, if we increase that, all other factors are remaining same. So, this will achieve at a lower So, this is IL 2, IL 3, IL 4, IL 5, IL 6. So, this many 6 velocities we are considering, and accordingly I could see that V1 here in this particular case, V1 has the high speed. So, V1 equal to V2 equal to V3, or since we are taking italics. So, this is Roman we are considering. So, V4 greater than V5 greater than V6. So, correspondingly delta 1 would be less than delta 2, less than delta 3, less than delta 4, delta 5, delta 6. So, this will be the situation, and we are considering IL equal to dF C0 by delta, and C0 is the concentration of oxidant. Now, interestingly, IL 4 is exactly equal to I critical. Now, if we start from IL 6, let us say this concentration is started from IL 6, as we are increasing the concentration to V1. So, then if it is a freshly prepared surface with no oxide surface on the metal surface, oxide layer on the metal surface. So, that case, as we have discussed in case of the case 1, where case study 1, where concentration of oxidant is increasing. So, the mixed potential point or the corrosion rate will be in these locations. Now, once we cross the velocity 4 to velocity 3, that means the velocity is increased from 4 to 3, immediately the corrosion point will reach here. So, and then after that, if we keep increasing the velocity, IL does increase, but my passive region would be always at this location. And remember, when we have this kind of situation, that the passive film is very strong in nature. So, that with that increase in velocity, the passive film does not break down easily. At the same time, even it breaks down, still immediately it starts reforming, because all the time I have to maintain this particular point where I C equal to I A. So, the corrosion rate would be with velocity. If I see, this is corrosion rate. If I try to see the corrosion rate when it was 6, I am starting from 6. So, this is 6. So, velocity is increasing like this. Okay. So, at this point the corrosion rate would be here, then corrosion rate in case of 1, 6, 5, it will be increasing, 6, 4, it will be here, this point, which is nothing but I critical, and then once we reach 3, the corrosion rate would drop down to the passive region corresponding to the passive current density. So, this is I P, since this is I P, and then if we increase the speed, the corrosion point should be this point only all the time. So, the distribution or the variation of corrosion rate would be this one. So, I could see that the corrosion rate varies. Initially it increases, and then once it crosses I critical, I will have the existence of IP, which is a very low current density, or this particular zone is nothing but stable passivity. So, this is the analysis, and now if I try to see the concentration, if the velocity decreases in this way, velocity is increasing. So, if it is this is decrease, now the pattern would be when it reaches to 4, if the oxide layer does not get dislodged, my corrosion rate point would be when the velocity is corresponding to V4, it will be here. Now, after that, even if we go to 6, which is the lowest velocity, if the oxide layer is not getting dislodged, I will keep that passive layer. So, when we return, the return point, that means the velocity is decreased gradually from 1 to 6, I could see that every place I will get passivity, because the surface is not getting disturbed. But if the surface is disturbed, let us say at 4 point, if it is disturbed, this will reach to this, or at 5 point, if it disturbed, it will reach to this, or 6 point, if it disturbs, it will reach to this. So, this way we can analyze the effect of concentration polarization on the active passive metal corrosion rate. So, let us stop here. We will continue our discussion on the active passive metal, and we will take 2 more instances. One is the influence of alloying on the attainment of passivity in some critical metal like titanium, and the second part is we have to also talk about anodic protection of metal, where in the anodic side, if you polarize, we do get a lower corrosion rate and protect the structure. So, let us stop here. We will continue our discussion in the next lecture. Thank you.